Alright, welcome back to chapter 4 of network information hiding. So in this chapter we will discuss network covert channel fundamentals. This figure is taken from our book that I mentioned in chapter 1. It shows how information concealment in communication networks can be divided into three components. First of all, we can hide the identity of communicating parties. This is realized with anonymity techniques, while we could also hide the content of a communication. This can be done with cryptographic techniques. We encrypt the content, then it's not perceivable anymore by third parties. However, we can also hide the communication process, and this is actually what we deal with in this class. And we use information hiding techniques to this end, and we can perform two different things here. So first of all, we could perform traffic obfuscation, where the overt type OT would be destroyed because when we apply traffic type obfuscation, we modify the carrier to conceal the characteristics of the transmissions. For instance, we could let a secret data transfer in the Tor network appear like typical HTTP traffic. That would be traffic type obfuscation, and there's a strong overlap with network steganography, but this class is on network steganography, where we do not modify the characteristics of traffic in the sense that we want to conceal the characteristics of the transmission, but we want to conceal the secret transmission's existence. And this is what network steganography does. So the covert text, the CT, blends with the overt text, OT. I like to highlight a few differences between traditional and digital media steganography. I won't repeat all the fundamentals from chapter 1 here. You already know the terminology. However, the problem was that covert channels arose in the 70s and the first network covert channels in the early 80s, or no, late 80s, I think. And the problem here is that they describe how information can be hidden in network transmissions without necessarily only focusing on the policy breaking aspect. It's really also about hiding data, which is a subject of steganography. And around the year 2000 and the early 2000s, the term network steganography was proposed to describe essentially that the kind of methods that hide data in network transmissions. So we had network covert channels and network steganography methods essentially describing the same thing. This was mostly then detached from the multi-level security and policy breaking concepts and context. It was both focusing on hiding the existence of a transmission. For this reason, network covert channel and network steganographic channel mean actually the same, but were handled separately, and that inconsistent terminology led to some scientific reinventions, because some method proposed for a network covert channel might be also proposed for network steganographic channels, but actually it's the same thing. It took several years till the community agreed on a unification here and a strong link, because it was agreed that the steganographic method creates a covert channel, which is actually rather clear when we think about it. So the network steganography research provides the method, but what it creates is a covert channel. That means that covert channel methods are network steganography methods, and that network steganographic channels would be covert channels. A bit more terminology here. So when we have some covert data, then it's the carrier, and we place the covert data in it. The cover object is now called at least often a carrier. Sometimes we also just speak of a network flow, network packet, and so on, frame, segment, or datagram, depending on the protocol and context. And we have the advantage of a constant transmission, so we can achieve permanent data leakage. This is, however, what I already explained in chapter 1. There's also something that I want to say about advantages. So first of all, it's difficult to analyze all network data from a forensic perspective. So only if you record everything, you can analyze all the network data, but it disappears if not recorded. It has a small delay, which is an advantage for the steganographers, and with the growth of the internet, the grow too. So there's an ever-increasing number of protocols and traffic that allows information hiding to be deployed in such carriers more easily. Here's a trivial example using the Scapy tool. I really recommend you to play around with this tool and the Wireshark traffic recording tool, because it visualizes network transmissions very nicely, and you can play around quickly with some methods of information hiding that require no responses and things like that. So if you just want to send packets, then it's a good thing. So what I did here is I just modified the reserved bit of the IP version 4 header, which is an unused bit essentially, and I hide some either the bit is set or not, depending on the IP flags that I set to 4 or 0, which will then trigger this bit to be set or not. I just attach an ICMP header behind the IP packet here. This is done with this slash and then the protocol. You could also write, for instance, TCP or UDP here, and you could also attach an HTTP header behind TCP, for instance. I think source and destination are clear, it's just the addresses. And so we can see here that the forward packet, for instance, has the value flex values 4. So the forward is set here, and the reserved bit is for this reason set. And the covert channel, a trivial covert channel, would then alternate between zeros and ones. A more sophisticated channel is Ping Tunnel. It's a public tool. You can download its source code. It's open source, and it's so what it does is, if you have a client, for instance, in an organization that wants to transfer data to a destination via TCP, but a direct TCP transmission is not allowed, then it tunnels the data through ICMP echo payload to a proxy system that is then allowed to send TCP packets to the destination. So it decapsulates the TCP packets and forwards them. It also receives the response and tunnels the response back to the client via ICMP. So we have some, let's say, Ethernet frame or whatever underlying protocol we have, IP and ICMP header, and then in the echo payload we have Ping Tunnel. But Ping Tunnel has also some additional data in it. It's not just the TCP segment, which would reside in the data part here. It's a whole header. So first we have a magic byte that has a value that indicates the presence of a Ping Tunnel packet. Then we have some addressing information, IP port, we have a connection state, we can acknowledge data, we have a length field for the data, and a sequence number and a reserved value or reserved bit. So this protocol works rather nicely, and have a look at it if you are interested. What is important is that you understand the concept that you can put such protocols. We will discuss such protocols in detail in a later chapter, in chapter 6, and that they can be used for circumvention of blocked connections. So for instance, a journalist but also a malware could use such a technology to route around a blocking attempt, such as a firewall that blocks TCP connections to the destination. We improved this tool because it has some limitations. In this journal paper, where we describe how the embedding and use of this tool can be made more reliable and secure. So, I want you to understand some core types, some fundamental types of network covert channels. First of all, we have local and network covert channels. This is what I already talked about. Local covert channels were dealt with in chapter 2, and the network covert channels, of course, the ones that were that transfer data over network connections. Or network transmissions. Connections is a wrong word because we don't always have a connection-oriented communication. Sometimes you just send a single packet. There are storage and timing channels. I also talked about this, and in a network context, storage channels usually modify some protocol headers, but also sometimes padding fields, or increase protocol size, packet sizes, things like that, while timing channels modulate the temporal behavior of the network transmission. We have noisy and noise-free channels. So noisy channels are typical channels that because most channels are subject to some kind of noise, in the sense that the value that is written is maybe disturbed. For instance, in a timing channel that uses delays between succeeding network packets, there's jitter on the network and so on, and maybe packets get dropped or whatever, and or take a different route to the destination. So that means that the exact timing that the sender used won't appear at the receiver side, at least not necessarily. So there's a little bit of noise. Noise-free channels, however, are kind of perfect. So there's no noise. If I would assume that every packet reaches the destination, and that, for instance, I set or clear the IP version 4 headers reserved field, like shown in the trivial example, and if I am sure that this value would never be changed by some intermediate node, then I would consider this as a noise-free channel, because there is no influence during the transmission on the channel that disrupts the information that I stored or encoded in that channel. There are some fundamental types of network covert channels, besides the fact that there can be noisy and noise-free and storage and timing network covert channels. I added typical questions about these fundamental terms to the exercise so that you can train your understanding a bit about of these terms. So we have passive and active covert channels. With an active sender or receiver, we have an element that creates the carrier traffic to embed the covert traffic in it. So that means the covert sender that I derive always with CS in this class, and the covert receiver that I always abbreviate with CR in this class, use a traffic that is, first of all, generated by the covert sender and not by some legitimate user, with the purpose of embedding the hidden information in it. And the covert receiver is also the actual destination of that data. So there's no legitimate destination that would do something with the data. However, there's also a passive scenario feasible, where when we have a passive covert sender, then it would wait for some legitimate user to generate some legitimate traffic, and then piggyback this traffic while being on the path to its destination. For instance, the covert sender could be a gateway on the path between the legitimate user a legitimate sender and a legitimate destination. And the covert receiver, if it's a passive one, would also extract the information on its way to the destination, to the legitimate destination, and that would be then a passive receiver. There's also semi-active and semi-passive as terms for describing this process. So this was introduced by Lamshoeft et al. In 2020. And so when we have a semi-active network covert channel, then we have an active covert channel sender, but a passive receiver. If we have a semi-passive one, then we have a passive covert sender, but an active receiver. There's also work on unintentional covert channels, which we refer to as side channels. So as mentioned in earlier chapters, a side channel is a channel that sends data but without sending intentions. For instance, a cryptographic algorithm that leaks information about the key through its runtime, or memory consumption, or things like that. This also works, for instance, with web applications, as shown by Sebastian Schinzel, who's a professor at University of Applied Sciences in Münster. And during his PhD thesis, he exploited a side channel that works as follows. So if you have a covert receiver and sender at the same time, actually, then the sender can probe some target information to the covert receiver. So how does this work? Let's assume this target is a web service where you have to log in. You send your username and your password. Now, the covert receiver would send many usernames and password combinations to brute force the target, because it wants to try figuring out whether some combination of username and password would exist. Now, what would happen? Let's assume we send the user Adam and the password so and so. Now, it first checks in its, let's say, SQL database whether the user Adam exists and whether the password, and if it exists, it checks whether the password matches some hash value that is transferred, and then it sends back the response and says, well, invalid credentials, or hello, welcome Adam, you successfully logged in. Now, what happens here is that, of course, first the username must be checked, and only if the username is present, the password will be checked. That means if the username exists, the response will take longer because the password has to be checked too. Now, what this means is if you send a username many times and measure the response time, so the time delta between sending your request and receiving the response, and you compare the time it takes to get a response for different usernames, you can see whether a username exists, because the response will take longer for a username that exists because the password has to be checked too, and that would be a leakage of information through a side channel. In particular, this is a timing side channel because it's based on the timing of the transmission and response. So this works as well. And then there is another type of distinction, namely between direct and indirect covert channels. So direct covert channels are those where the covert sender sends data to the covert receiver directly, so that the hidden information is directly encoded in a way that the the covert receiver, can extract it. There's, however, also a different method feasible, and that's an indirect covert channel. So this would work, for instance, over the web server load. If the intermediate node would be a web server, let's say it's embedded web server with low computing power. So the covert sender could receive over time either many or only a few requests to the web server. So this is indicated by this line here. So if it's higher, then let's say there is more requests per second, and so it influences the system load on the intermediate node, and now the covert receiver at the same time can pull data from the intermediate node and measure the response time. So when the intermediate node is busier, then response time will take longer, and so the system load can also be inferred by the covert receiver, and that would be an indirect network covert timing channel. Now, we know a few types of covert channels now, but we also need to study how we can measure covert channels. Well, I don't want to discuss all the aspects here of measuring covert channels, because this will be covered in more detail in the class information hiding. So the other part of this module, which is taught by Professor Keller, and he will introduce fundamental terms like capacity, bitrate, bandwidth. So how much information or data can be transferred per time is the question. In general, I assume you have a basic understanding of these terms, but I won't conduct any calculations or something in this class, at least in a very limited manner. Undetectability or covertness is how detectable a covert channel is. However, there are different ways to describe this. And robustness is only valid for noisy channels. It means, or it explains how fragile a covert channel is. So how much distortion of the carrier can be survived, and the information still being present. The secret information, of course, is meant. But I want to discuss some other measures that are typical for network covert channels, because these here that I listed on this slide are essentially important for all types of covert channels, also for local covert channels, and also for instance, robustness is a key criteria for digital watermarking. Okay, so how describe in general coveredness? Well, it's the coveredness is always proportional to the capacity of the medium minus transmission rate. So if the whole capacity of a transmission medium, for instance a network packet or an audio CD, is used, the coveredness is 0, which leads to a trivial detection, because we just overwrite, for instance, more or less all the things we can overwrite and hide the data in it. However, if only a tiny fraction of the capacity is used, the coveredness can remain close to 1. And the higher the capacity, of course, the more data we can embed, or the more information we can embed. And well, it's always a trade-off. I mean, if you have a higher transmission rate, then of course your data is transferred in less time. But you always risk detection, because your detectability increases when the covertness decreases. Extension to these fundamental terms is steganographic cost, in short SC here. And this is specific to network information hiding. It's a measure of degradation or distortion of the carrier that is caused when the steganographic method is applied to the carrier. The calculation depends heavily on the context. So for instance, for lag steganography, that is one that drops packets in a specific way to signal hidden information. So you have a stream or a flow of network packets, and you drop selected packets to encode a hidden message, and the receiver just checks which message is dropped. So the steganographic cost can be calculated using the mean opinion score there as a difference in quality of voice signal without and with this lag method being applied. So over time we would check what's the delta mean opinion square between both scenarios, so with and without the lag method being applied. So for retransmission steganography or RSTEG, where it's basically the opposite of lag. So the idea is you mimic the behavior of certain protocols such as TCP that have a retransmission functionality, where they assume that the segment got lost and you just retransmit it so that it reaches the receiver and an acknowledgement is received. So one can mimic this behavior in a steganographic manner. There's quite a lot of research about this. And however, the difference is in the appearance here of retransmissions. So in the easiest way, you would either for the whole flow or for a time window, here it's calculated for the whole flow, calculate the retransmission, total retransmission steganographic cost by the difference in retransmissions, which is called RD here, and that would be the difference between the retransmissions in a network with RSTIC being applied and without RSTIC being applied. Of course, this is only really meaningful if you do this over a longer period of time, because in normal networks, retransmissions are, at least nowadays, rather rare. We performed some experiments on retransmission steganography in a 2018 paper over different internet connections, and it's highly heterogeneous how many packets are actually dropped. So you need to calculate steganographic cost in a specific manner for each flow or network environment at least. Now, if you have a typical IP packet, for instance, or any other carrier, we can divide it into subcarriers, and usually different steganographic methods are exploited for different subcarriers. For instance, one subcarrier, an IP header, could be the reserved bit, another one could be some options header. And if you want to calculate the total steganographic cost for that carrier, you need to sum up the specific cost that you add to each subcarrier using all your methods. So now we learned all the basics that are required to understand the next chapters. Chapter 5 will be about hiding patterns, and that chapter we will learn how or what kind of methods exist to hide data, and combining chapter 4 and 5 will then allow us to understand sophisticated network steganography methods that I will deal with in chapter 6.